Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the overdamped, critically damped, and underdamped criterion for the source-free series RLC circuit, where this is a build-up on the previous video I made called the source-free series RLC circuit clearly explained, which I will post in the top right-hand side corner of this video, where the criterion for the overdamped system is when this alpha, or my damping factor, is greater than this omega naught, which is the resonant frequency. For a critically damped system, the alpha is equated to omega naught, and for an underdamped system, the alpha is less than omega naught, where again alpha is equated to this resistance R over 2L, and again this is my damping factor, and omega naught is equated to 1 over the square root of my inductance times my capacitor. Again, this is my resonant frequency, and this is for a source-free series RLC circuit. So the whole purpose of this video is to take each of these cases and solve for I of t, and also graph I of t to see what each of these cases are doing and see how we can compare each of these cases to real-life applications. So for the first case, where it's the overdamped case, my criterion is that alpha is greater than omega naught, or I can say that R over 2L, or alpha, is greater than this 1 over the square root of LC, where then the square root of LC is greater than 2L over R. So then I can say that C is greater than 4L over R squared. And this here is an important parameter, call it the critical capacitance. To begin solving for I of t, we say that I of t is equated to this A1 E S1 of t plus A2 E S2 of t. If we go ahead and plug in our parameters for S1 and S2, which we discussed in our previous video, we're going to get that this is going to be A1 E to the minus R over 2L plus square root of R over 2L squared minus 1 over LC times T plus A2E to the minus R over 2L minus the square root of R over 2L squared minus 1 over LC times T. Where again, this here is S1 and this here is S2. And since R over 2L is greater than 1 over the square root of L times C, we can say then that therefore S1 and S2 are negative and real. And I hope we can all see that, but it's because what's in the square root bracket, so this term here, so let me write it out, R over 2L squared minus 1 over LC. If this term is greater than this term, this will never be negative. As a result, again, S1 and S2 are only going to be negative because of this term here and real, which we stated up here. So to conclude, therefore, I of t is simply just this A1 e to the S1 t plus A2 e to the S2 t, where its graph looks something like this. So if this is I of t and this is t going to infinity, let's take that at I of 0, this is 0, and let's take this decaying function as a reference, where this is e to the st. My function for my current will be 0 until here, and then it will lift up and go like this. And some things we can state for an overdamped case is we can say that the energy dissipates into my resistor slowly. So if you remember, that's where my heat is being dissipated, right? Or my energy is being dissipated. It's to my resistor. and in this case is being dissipated extremely slowly. So energy dissipates into the resistor slowly. All right. And we also say in an overdamped case, my resistance is very high. So very high resistance. And two examples which you might have experienced in your day-to-day life are an emergency door. So emergency doors normally have a heavy spring, so the door slowly closes. It's not fast. And a hand sanitizer pump. So when you push down on the hand sanitizer pump, it doesn't spring up immediately. It takes its time. So these are two cases of overdamping systems. So now the second case, which is the most important case, is the critically damped. And we say that alpha is equals to omega naught for its criterion, where alpha in this case again is R over 2L, which is equated to 1 over the square root of LC. So then we say that the square root of LC has to equate to 2L over R, where again, so my critical capacitance is equated to 4L over R squared in this case. Just as an observation, we said that S1 and S2 is equated to minus alpha plus or minus the square root of alpha squared minus omega naught squared from our previous video. So if these two are equated, that means that S1 and S2 are simply just equated to minus alpha or minus R over 2L, meaning that we can write our I of t as A1 e to the minus alpha t plus A2 e to the minus alpha t, or simply pull out A1 plus A2 and we're left with e to the minus alpha t, or A1 plus A2 can simply be a constant, which we call A3, and we're left with e to the minus alpha t. So now the reason why I wanted to do this is to show you that this is not the correct answer. And the reason why it's not the correct answer is because we need two initial conditions, right? The first initial condition is associated with my capacitor, and the second initial condition is associated with my inductor. And as a result, one constant isn't enough to solve for the circuit. Another way to think about this is to say that since we have two current initial conditions, so I at time 0 and I prime at time 0, these two cannot be satisfied by one singular constant. Therefore, there's something wrong with this solution here, and it is incorrect. And in order to find out the real solution, we need to go back to equation number 4 from the past video, or the second order original differential equation, which was d squared I over dt squared plus r over L di over dt plus 1 over LCI has to equate to 0. So let me go ahead and plug in alpha and omega naught into these two terms. So then I'm going to be left with d squared I over dt squared plus 2 alpha di over dt plus omega naught squared I is equated to 0. Let me go ahead and plug in my criterion, which says to take alpha as equals to omega naught. So then we get d squared I over dt squared plus 2 alpha di over dt plus alpha squared I is equals to 0. So now the solution to this problem becomes a little bit more tricky, but what I'm going to do here is I'm going to rewrite this as d squared I over dt squared plus, I'm going to separate this term into alpha di over dt plus alpha di over dt plus alpha squared I is equals to 0. Between these two terms, I can pull out a d over dt, and I'm left with di over dt plus alpha I plus, if I pull out an alpha within these two terms, I'm left with a di over dt plus alpha I is equated to 0. And let me call this equation number 1 for this video. I'm hoping this is making sense so far. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Let me go ahead and call this term here f. So again, it's the same as this term here, f. So if I say that f is equals to di over dt plus alpha I, so therefore, from equation number 1, I'm left with df over dt plus alpha f is equals to 0. And I hope this manipulation of my terms makes sense, where again now this is a first order original differential equation, and we know that the solution to this, we know that f has to be a1 e to the minus alpha t. And before we continue, let me call this here equation number 2. In the next slide, because I'm running out of space, I'm going to write out equation number 2 and equation number 1, and we'll continue from there. Okay, so now we have equation 1 and equation 2 here, and we need to remember the goal of our entire problem, right? For this critically damped system, we want to find I of t, or we also call this just I. So this is the goal. So we shouldn't forget this. So now let me go ahead and rewrite equation 1 again. So again, this is d over dt of f. I'm plugging in equation number 2 into here, right? Plus alpha of f is equals to 0. And we said that the solution for f in this situation is my first order ODE solution, which says that it's a1e to the minus alpha t. And this is nice because we have a solution for f here and a solution for f here. So let me go ahead and equate the two together. So we know that a1e to the minus alpha t, or this term here, has to equate to di over dt plus alpha I, or this term here. Let me go ahead and multiply this by 1 over e to the minus alpha t. And again, I explained this in the last video, but I can put this in the denominator because it would never go to 0. So then when I do this, I get a is equated to e to the alpha t di over dt plus e to the alpha t alpha I. And it's not easily visible, but this here is equated to the product rule of e to the alpha t and I of t. Again, I just call this I. So to prove this, I'm going to take an example here. So imagine I have d over dt of e to the alpha t times I of t. Again, I can just call this I. So this is equals to, I leave my first term alone. So this is e to the alpha t. I take the derivative of I of t. So di of t over dt plus I take the derivative of e to the alpha t, which is simply just e to the alpha t again. And I leave my second term alone. So alpha I of t. And again, this is just e to the alpha t di over dt plus e to the alpha t alpha I, which again is equated to a. Again, is equated to this term here. All right, so a. And again, with this example, I'm just showing then that this term is in fact the product rule of e alpha t times I of t. So now let's wrap this up. So a is equals to d over dt e to the alpha t I of t, or simply just I. What I can do is take the integral from 0 to t dt of both sides, 0 to t dt. On my right hand side, this cancels out with this. This integral cancels out with this derivative. So then I'm going to write this term on the left hand side now. So I'm left with e to the alpha t times I is equated to the integral from 0 to t of my constant here a is simply a, let me call this a1 t plus another constant, call it a2. So then now to solve for I, again, which is just I of t, I get, let me write a2 first, plus a1 of t e to the minus alpha t. And this here is a very, very important solution. Again, as you can see, I'm satisfying my initial condition for my capacitor and my initial condition for my inductor. So I have two different constants. And again, the mathematics to get to here, all you need to do is do it at least once in your life, understand how to get there, and then that shows to yourself or proves to yourself that you've done it before. If you have any questions on how we got here, please leave any questions or concerns down in the comment section below, and I'll be sure to get back to you. If we wanted to plot I of t, we say that this is I of t, this is t as t goes to infinity. If I consider that I have a decaying function, let me call this decaying function e of minus alpha t. And let's take that my current has been 0 all the way to I of 0 is equals to 0. What's going to happen? It's going to shoot up and then start to decay. For this case, we say that there's little to no oscillation. And we also say that my energy is dissipates as fast as possible to the resistor. When you're designing any system that you might be working on, this is the just right case or the ideal case. So the critically damped case is where you want to be. So what most engineers will do is they might increase or decrease the resistor value in order to satisfy this case by putting resistance in series or in parallel. And essentially, it's simply because we dissipate all our energy ideally through our resistor. Some examples you might think of is a food scale, right? When you put a food on your food scale, like your chicken or your rice, it shoots up to that specific weight immediately, right? So that's the ideal case. You don't want it to be oscillating within the weights and then saturating to the ideal to the weight of the chicken or the rice. You want it to shoot to that weight and stay there as fast as possible. Another one that's probably in front of you right now is your mouse click, right? When you click on your mouse, it jumps back up to its original position. You might hate to use a mouse that you click and then it gets stuck or it comes up slowly, right? So you want a mouse that goes right to its ideal or its start position as soon as possible, so the energy is dissipated within its springs or its mechanics. So I hope these two examples make sense and help to visualize what the critical damp looks like. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. So for the last case, which is the underdamped case, which might not be as tedious as the critically damped case, we get to know that alpha, which is r over 2L, has to be less than 1 over the square root of LC. So again, we get that the square root of LC is less than 2L over R, which again, C is less than 4L over R squared. And again, this is my critical capacitance for this case. Let me go ahead and write S1 and S2 separately. So S1 is equals to minus alpha plus the square root of minus omega naught squared minus alpha squared. And since this is a negative, it becomes minus alpha plus j omega d, where this omega d is my damping natural frequency. And the reason why it's damping is because it depends on my resistor value R. So then we could say that S2 is equals to minus alpha minus the square root of minus omega naught squared minus alpha squared, which again is equated to this minus alpha minus j omega d. So therefore, if we write out our I of t, we say that this is a1 e to the minus alpha minus j omega d t plus a2e to the minus alpha plus j omega d t. What I did essentially is I pulled out a negative here. So then this becomes like this. And if I pull out this negative here, this becomes like so. I hope that makes sense in terms of this term here and this term here. So what I'm going to do next is pull out this e to the minus at from this term and this term here. Don't forget the t. So what I'm left with is e to the minus alpha t times a1e to the j omega d t plus a2e to the minus j omega d t. I'm going to go ahead and use Euler's identity and say then that e to the j theta is equals to cosine theta plus j sine theta, and e to the minus j theta is equated to cosine theta minus j sine theta. So in this situation, substitute theta is equated to omega d. So therefore, I get I of t is equated to e to the minus alpha t times a1 times cosine omega dt plus j sine omega dt plus a2 cosine omega dt minus j sine omega dt. I can pull out a cosine omega d term from here and here, and I can pull out a sine omega dt term from here and here, along with the j's as well for the sine terms. So then I'm left with e to the minus alpha t times a1 plus a2 times cosine omega dt plus j a1 minus a2 times sine omega dt. And finally, I of t is equated to e to the minus alpha t times, I'm going to call this term here, since it's a constant plus a constant, I'll just call it b1 times cosine omega dt plus, and I'm going to call this term here b2. So then this becomes b2 sine omega dt. And this here is your final solution for your I of t, or how your current behaves in an underdamped case for a source-free series RLC circuit. Okay, so a couple of things to note. We say that omega d is equated to 2 pi over t. So then that means that my period t is equated to 2 pi over this omega d. I'll go ahead and move this down just a little bit because I want to have some room here to draw my graph. If I draw this graph and it looks like this, where again, this is I of t and this here is t. If I go ahead and plot these boundaries, call this e of minus t, and there's a reflecting boundary here as well. And let's take that I of t was 0 all the way until I of 0 is equals to 0. So that's my initial condition. What's actually going to happen is it's going to oscillate between these both parameters and slowly go down to 0. Where my period from here to here, we talked about it being 2 pi over my damping natural frequency, omega d. So essentially we can say then that this is an oscillatory response. And a couple of examples which you see all the time is a bobblehead, right? It keeps going back and forth, and then until it finally dissipates and stops. Another example are what I call the ringing doors at a bar or a restaurant, right? The one that swings back and forth to prevent accidents going inside and outside of the kitchen to the restaurant. And the last one you might think of is something like a trampoline. A trampoline rings back and forth, oscillates until it stops. Okay, so if you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. If you liked the video, please give it a thumbs up, and please share the video to your colleagues and friends so they can also obtain the knowledge. And lastly, if you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.